Hello again. This is video lecture 4.4. The reading that goes with it in our textbook is chapter 4, section 5. The topic is uniform circular motion. So that's what we're going to talk about. Circular motion that apparently is of a very special kind because it's described as uniform circular motion. This is very important motion because there are situations in the world where things do move in circles, and we need to be able to analyze that motion. So in this discussion, we are going to use kinematics to describe mathematically uniform circular motion. And then later on, in chapter 6, we'll address the deeper question of how do you get a particle to move with uniform circular motion to begin with. But for now, let's not worry about how you get something to move with this in this special way called uniform circular motion. Let's just assume that we have a particle moving in this special way, and we want to analyze that motion. So first, first main key idea is what exactly do we mean in physics when we talk about uniform circular motion? We have to all be clear on what that means. Uniform circular motion, of course, means moving in a circle with constant speed. Right there, speed. So let me start right away with a sketch of what I'm talking about. I have drawn here below an XY coordinate system. Let's just imagine, for the sake of having something to visualize, that we're looking down from above on a flat tabletop, for example. And the x-axis is to the right on the tabletop, and the y-axis is going across, perpendicular to that, on the tabletop. And somehow we have managed to get a particle moving in a circle on this tabletop. And at the instant, at the snapshot shown here, the particle is located right there with the dot that's labeled particle. And the dashed trajectory there is the circle that it's moving in. Okay? And as we watch it, when we took this snapshot of it, the particle was traveling around the circle in a manner that you could call counterclockwise, going around like that. Okay? So imagine a particle going around and around and around on a tabletop counterclockwise against the way the hands of a clock would move. Now, a circle, as we learned in math, is described by a mathematical equation. And there are basically two key things you have to know to mathematically describe a circle. Where is its center, and what is its radius? So I have denoted in my picture the location of the center of the circle. I've marked it with an X. The whole circle, as you see, happens to be located in the first quadrant, and the center of the circle is where I marked with the X. That's some point in the XY plane with coordinates X sub C, Y sub C, C for center. And then the radius, of course, as you know, is the straight line distance from the center of the circle out to the particle on the circle. Notice the symbol I'm going to use for the radius in circular motion is a capital R. Now my particle itself, at the moment I took the snapshot, remember the particle itself is down where the dot is. It is lying on the actual circle, and it has coordinates that I've just labeled X comma Y because I picked a generic point on the circle. Okay, so with the coordinates of the center, X, C, Y, C, the radius, and the coordinates of the particle on the actual circle, X comma Y, here's the famous equation for a circle that you do need to remember if you're going to study circular motion. X minus X center quantity squared plus Y minus Y center quantity squared equals radius squared. So please note, this X right here is whatever this X is. This Y right here is whatever this Y is. XC here is whatever this value is. YC here is whatever this value is. The R is whatever the radius is. That's how those various quantities are related. That is the equation of a circle, which at some point you did learn in high school math. Okay, I'm going to get rid of now some of these markings I put on here. Okay. I will keep this little arc of a circle just to remind you that the particle is moving counterclockwise, pardon me, around this circle. Okay, back to looking at it at the moment I took this snapshot. Again, there's the particle right there. I've sketched two vectors in this picture. The particle's instantaneous velocity, that's the red arrow labeled v, and its instantaneous acceleration, that's the orange arrow labeled a. And the first thing to note, this is true for any motion, the velocity is tangent to the path it's moving in. In this case, it's moving in a circular path. So the velocity must be tangent to the circle and pointing in the direction the particle is moving at that instant. So it's very important that you understand in this sketch why the velocity vector is drawn the way it is. Right? Namely, right like that. It must be drawn as an arrow that is tangent to the circle, pointing counterclockwise at that instant. Okay? So that's the actual velocity vector at that instant. Okay? All right, now, here comes an interesting question for you. Something to think about. Uniform circular motion is what we're studying. Our statement right above, the key idea, says that uniform circular motion is the particular kind of circular motion when the speed is constant. Okay, if speed is constant and the derivative of a constant is 0, and the derivative of speed is acceleration, shouldn't the acceleration be 0? There's a flaw in that reasoning. I'd like you to pause the video and think about it. What's wrong with what I just said? And then come back and we'll talk about it. Okay? What's wrong with claiming that when a particle moves in a circle at constant speed, its acceleration is equal to 0? Well, here's the thing. Remember the definition of acceleration. A arrow, acceleration is a vector with a magnitude and a direction, is the derivative of velocity with respect to time. V arrow. And any vector, like velocity, has a magnitude and a direction. If either part of that vector changes, either its magnitude or its direction, then the velocity is changing. If the velocity is changing, then its derivative isn't 0. And acceleration is derivative of velocity. So the flaw in my statement earlier is when I said acceleration is derivative of speed. That's just plain not right. That's not how we defined acceleration. Acceleration is derivative of velocity. And speed and velocity are not the same thing. Okay, so acceleration is derivative of velocity with respect to time. If any part of the velocity vector changes with time, there's an acceleration. Now, let's keep thinking about this. So we said we're moving in a circle at constant speed. So isn't the velocity constant? No, we just said velocity and speed are not the same. How are velocity and speed related? Do you remember that? Remember, speed is the magnitude of the velocity. So if we denote v arrow with the absolute value symbol on it, then we mean the magnitude of the velocity. That's what we mean in physics when we use the word speed. The magnitude of the velocity. So apparently the particle is moving in a circle with the magnitude of its velocity constant. That is fine. But note that as the particle moves, its velocity always has to change direction so as to stay tangent to the circular trajectory. For example, go back to our picture. There was the particle at the moment we took the snapshot. A little bit later, the particle will have moved around the circle and will be over, say, at that point, right there. If I asked you to sketch the velocity vector when it's at that point, you should be able to do it, just a sketch. How would you draw the velocity vector at that new location? Answer, draw an arrow that's tangent to the circle, and in this case, pointing counterclockwise. That's the new velocity vector. That's a different velocity than the first one because the direction is different. The magnitude isn't different, but the direction is. So the velocity has changed. If the velocity changes, there must be an acceleration. And one of the most important parts in this section of Chapter 4, and I do hope you read it, Chapter 4, Section 5, Uniform Circular Motion, is where they derive the expression for the acceleration of this particle moving with uniform circular motion. And I'm going to tell you the two key things you need to know about acceleration in uniform circular motion. Its direction and its magnitude. Okay? Now that we know the acceleration is not zero. First, the direction. It's directed towards the center of the circle. There it is in my picture. Let's go back to where the particle was initially. You see the orange arrow labeled A? Right there? Notice it's drawn with its tail anchored at the particle, and notice what its direction is, towards the center point. A arrow, that's the direction of the acceleration, directly towards the center. So if I asked you to sketch the acceleration vector at that second location that I've drawn, you should be able to do it. How would you draw it? I don't have an orange color on my palette here, so I'm going to use purple. But how would you draw the acceleration vector for that second location? Just anchor it at the particle and draw an arrow towards the center and label it A with an arrow on top. That's the new acceleration vector. It always points towards the center of the circle. So if I gave you a different location for the particle, like what if it's up there on the circle? You should be able to sketch the V vector and the A vector. Right? V is tangent to the circle, and A points towards the center. Now, I'm not proving that, I'm just telling you that result. You want to see the proof? Read Chapter 4, Section 5. The other important thing is what's the magnitude of that acceleration? Right? That's also derived in Chapter 4, Section 5. And I'm just going to tell you the formula. And it's very useful if you have uniform circular motion. There it is, right there. The magnitude of the acceleration, which we now know is directed towards the center of the circle, is given by, take the magnitude of the velocity, square that, and divide by the radius. V squared over R is how we say it. Again, I'm not deriving that here. You can read in your book the derivation, and you should. You shouldn't necessarily just accept it on faith. It can be derived mathematically very clearly, and this formula then can be justified. The magnitude of the acceleration when a particle moves in a circle at constant speed is V squared over R, the magnitude of the velocity, i.e. the speed squared over the radius. Let's at least check that the units work, because we've never seen a formula quite like this before for acceleration. Let's take the units of V squared and divide by the units of R and see that we get units of A. Okay, so we're just checking units. So in the numerator we have V squared, meter per second, but we have to square that, so that's meter squared over second squared. That's in the numerator. In the denominator we have R, radius, that's in meters. So there are what the units look like. Meter squared over second squared over meter. That's equivalent to meter squared over second squared times meter. Then I can cancel 1 factor of meter in the denominator and 1 factor of meter in the numerator, and I'm left with the unit of meter over second squared. Those are the correct units for acceleration. So just on unit basis, I can tell that that's at least a plausibly correct formula for A. Just one more thing that you want to be aware of, because it is used a lot when physicists are talking about circular motion. This scenario, where we have an acceleration vector that is always pointing towards the center of a circle, is given a special name. When you have circular motion and you're talking about the direction towards the center of the circle, the adjective that is used for anything in a circle that points towards the center is centripetal, which is from the Greek for seeking the center. So you'll often hear physicists call the acceleration in this scenario centripetal acceleration. It just means that the acceleration points towards the center. Let me just say one thing. I hesitate to even bring up this word, but you probably have heard it in everyday life. And so it's already kind of lurking in the back of your brain. So I might as well bring it up to the front of your brain and then warn you about it. There is another word that people use in circular motion that is very similar to the word centripetal. Okay. It is called centrifugal, which means, by the way, pointing away from the center. I want you to, for this class, scratch that word from your brain. Please do never use it. We are not going to use it. Please note that this acceleration points towards the center, not away. Okay? All right, I'm going to scratch that word completely. Okay, I hope this is making sense. This is a very important kind of motion for us to study and understand. So let's start practicing. I have one more little tip to tell you as well. Let me bring up some more content here. Okay, here comes the next tip. Very useful thing to remember when you have uniform circular motion. Note first how I abbreviate. Uniform circular motion is a lot to write out. I type UCM for uniform circular motion. Remember, uniform circular motion means the particle's speed is constant. All right, one of the really useful things to know about uniform circular motion is what is called the period of the motion. All we mean by that in physics is the time to complete one revolution, the time to go around the circle exactly once. That's called the period. That's often a useful thing to know. Since it's traveling at constant speed, the time to go around once is just the distance it travels, that's the circumference of a circle, divided by how fast it's going, its speed, its magnitude of velocity. There, I said it in words. Here it is in symbols. Please note this. You need this just as much as you need A equals V squared divided by R when you study uniform circular motion. The period of the motion, note the symbol please, capital T for period, not little t. Because capital T for a given uniform circular motion problem is a constant. It's just the amount of time to go around once. Capital T, the period, is the circumference divided by the speed. The circumference of a circle is 2 times pi times its radius. And I'll use the symbol italic V for speed, not V arrow, that'd be velocity. Okay? So capital T equals 2 pi r over V. Very useful. Now let's start practicing studying uniform circular motion. I'm going to do one with you in our video here, and then I'm going to give you one as a class engagement exercise. Here is the scenario. This figure shows, kind of grouped together, 4 different tracks that a particle can move on. Actually, the particle in this case is a train, so think of these as train tracks. And all of these tracks, the key important part of them is the curved part. And the curved part in all 4 tracks is either a half a circle or a quarter of a circle. And we're only interested in when they are on that curved part. That's the only part we're going to be focusing on here. Now the train is moving around these tracks at a constant speed. And it's the same constant speed no matter what track the train is on. We are to rank, another ranking exercise, the tracks according to the magnitude of the train's acceleration on the curved portion, greatest first. Okay, so there's track 1, track 2, track 3, and track 4. We are to rank the acceleration magnitudes, biggest down to smallest. Okay, so I want you to pause the video and think about that for yourself for a minute, and then come back and we'll talk about it. Okay, welcome back. First, did you go in your brain to the formula for acceleration magnitude for uniform circular motion? Because that's what it's asking us to rank. So this is the formula. Acceleration magnitude, A arrow magnitude, is V arrow magnitude squared over radius. Now that's my careful way of writing it. I might as well just erase that right now and show you the shortcut way of writing it, since that's the way most physicists would write it. Just a plain old A equals a plain old V squared over a capital R for radius. When you write the A and the V with no arrow on top, you mean magnitude. Magnitude of A equals magnitude of V squared over radius. Note, for all 4 tracks, the magnitude part of the V, the speed, is the same. So the only thing that's going to be different for the tracks, apparently, is the radius when you're on the curved part. So why don't we first rank the R's? Let's do that, okay? And I claim you can do that. You might not be used to looking at little drawings like this, but they're just ways to show parts of circles that happen to correspond to train tracks. But we ought to be able to rank from biggest to smallest the radius of those curved tracks, the R. Okay? All right, and these dashed lines are trying to help you do that. Do you see which curved portion has the biggest radius of the 4? Did you say track 3? Because that curved portion has a radius, I'll sketch it. There's its center out to the edge. That blue line I draw right there, that's the radius for curve 3. Okay, and that's the biggest radius. Now let me erase. What's the next biggest radius? Do you see? Did you say curve 4? Its radius is right there. Just drew it right there. Isn't that half the radius of track 3? Okay. Do you see another track that has the same radius as track 4? Did you say track 1? Yes, it's only a quarter of a circle, not a half of a circle like 4 is. But in its quarter circle, that dashed line there is trying to help you see that there's its center and there's its radius. Same radius as 4. It's just drawn in a slightly different location, but it's got the same radius on its curved part as 4. So what's the track with the smallest radius? Well, it must be 2, because that's a very tight curve there, isn't it? And this dashed line right here is trying to help you see there's the center for 2, and there, right there, is the radius for 2, which is very short as far as this picture is concerned. So let's rank our radii for the 4 tracks. The biggest is 3, so I'll denote it like that. The biggest is the radius for 3. It is bigger than, now the next thing we have is a tie, don't we? The radius for 1 and the radius for 4 are equal. So that R1 equals R4. And that's bigger than the radius for 2, that's the smallest. So R2. Do you see I ranked the radii? 3 is biggest, 1 and 4 tie, 2 is smallest. Now I contend you're ready to rank the acceleration magnitudes. You see how to do it? Pause the video if you need to think about it a minute. Okay, so what's the ranking of the acceleration magnitudes? Did you say the acceleration magnitude ranking is exactly the reverse of the radius? Exactly switched. A2 is the biggest acceleration, and then A1 and A4 tie, and then the smallest is A3. Why? Where did that come from? From the formula over here on the left. A equals V squared over R. The R is downstairs. The bigger the R, since it's in the denominator, the smaller the A. So here then is our ranking for the acceleration magnitudes when the train is on the curved part of the track. And it's biggest for track 2 because it's the tightest curve. Okay, so the last thing on this video is to give you a class engagement exercise to do where you can type in your answers on Blackboard. Okay? All right, let me explain what I want you to do. In this figure, we have a particle P. You can see it there, the red dot, and it's labeled P. And it moves with uniform circular motion in the circle. The circle is drawn in green. You can see that it's centered on the origin of an XY coordinate system. So we actually put the circle at the origin of an XY coordinate system. We're just going to ask you some questions, A, B, and C, and I want you to go to Blackboard for the class engagement exercise assignment for this video, and by A and B and C, you just type in your answers. Here's the first question. Note that in the picture, we happen to take a snapshot of the particle as it's moving. And although you don't need this to answer the question, maybe to help you visualize, let's just pretend that the particle is circulating counterclockwise, okay? As it goes around the origin, just to help you visualize. The particle is circulating counterclockwise. When we took this picture, flash, you see where the particle was, particle P, the red dot. The picture is also drawn the position vector as a blue arrow, R arrow, from the origin out to where the particle is located. And that makes an angle theta with the plus x-axis, as you can see. And since theta is measured counterclockwise, theta is a positive angle. Of course, the point P is moving around and around and around, so you have to visualize the R vector swinging around to always follow the particle P. And what I'm not drawing on here, but you should be able to, is also you should be able to draw the velocity vector at any given location on the circle and the acceleration vector at any given location on the circle. So those aren't drawn here, but you should be able to draw them, those arrows. All right, with that in mind, here are the questions. Question A. At what values, note the plural, of the angle theta is the y component of the position vector, you could call that r sub y, greatest in magnitude? At what values of theta is the y component of the position vector greatest in magnitude? So your answer for A will be theta equals, and you'll give me angles. B, at what values of theta is the y component of the velocity vector greatest in magnitude? At what values of theta is the y component of the velocity vector greatest in magnitude? And C, at what values of theta is the y component of the acceleration vector greatest in magnitude? Please give all theta values as positive numbers. In that range. 0 inclusive, up to 360. So answer those questions for me, please, for class engagement on Blackboard. We will be talking in class about uniform circular motion to give you a chance for more practice. But that's all for this video.